Hi, we're going to find out where a chess knight can move from a given starting position. There are different ways to attack this problem, and they fall into two main categories. We could start with the starting position and compute all the places where the knight can move, or we can consider every possible position on the board and ask ourselves whether the knight can move there. And this latter method leads to a simpler solution. So let's try that. As an example case, we're given position 5-4, but let's not actually use that for now. We're just generating a chessboard. This is a lambda and the index generator, which generates an array of shape 8-8. That is 8 rows, 8 columns, and every element is the position of that element, or the indices of that element. So every element is a vector of 2 elements because there are 2 dimensions, and it has then the index for that position. Now, if we subtract from every element the entire argument, we get the distance vertically and horizontally from each position to the starting position. And we can spot our starting position here by being 0, 0. Of course, there is no difference between the starting position and the position where, well, we are starting, and neither vertically nor horizontally. And what we're after are the valid moves for a knight, which you could see as moving 1 step in one direction and then 2 steps in the orthogonal direction, or the opposite. It's the same thing, of course. It's an L shape. So we could move 1 step right and 2 steps up, or we could look at it as 2 steps up, 1 step right, or we could go 1 step up, 2 steps right, and so on. 2 steps to the right and 1 step down. What is common for all of these we can spot is that, not that one, is that they all have a difference from a starting position that has the numbers 2 and 1, although they may be negative or not. So we could generate the list of all the differences. So we would start with -2, -1, and then -2, 1, and then -1, 2, and so on and so on. That would be a very long list, and we could then look up to see if for each difference whether it's a member of that list of permitted distances. But since that list is very long, we can shorten it a bit by taking the absolute value first. Now all the places we can move to are either 1, 2 or 2, 1. So we can look with membership, but we want the lookup array on the left, so we swap the arguments of the membership function, and then it has to be either 1, 2 or 2, 1. So now for every absolute value differences in this table of differences, we look up if it's a member of that, and that gives us a Boolean array indicating the positions where our knight from the middle here can move. Of course, we're not interested in this Boolean array. We want the indices where it is true that it can move, and for that we have the where function, which gives us the indices of the trues. And this is a solution, which is pretty elegant, but I think actually there is a neater solution. So if we cut back again to where we have our distance table, then we can use a little bit of mathematics. The Pythagorean theorem says that in a right triangle, the 2 shorter sides, if you take the lengths and square them, then if you add them together, you get the square of the diagonal. Now, this might not look like we're dealing with triangles, but actually, to move from the starting position and up here, we could see it as moving in a triangle with a side that has length 1, it's 1 step to the right here, and a side that has length 2. It's 2 steps up, and so on. The order of them doesn't matter because it's just a sum. So we can start by squaring the distances here. And then it doesn't matter which sign they have either, because you square a negative number, it becomes positive too. So one way to square is to multiply by itself. So multiplication, and then the same symbol that we used for commuting the arguments or swapping the arguments, we can also use for what I like to call a selfie, because it looks a little bit like a selfie face. So this is self-multiplication. So now all the values have been squared, and we can see here that now we're looking for all the places that have a 4 and a 1, or 1 and a 4. Now we can sum, so there's a plus reduction, each one of them. And here we can see that the places we can move to are the ones that have 5 as the total sum. So we're not actually interested in the length of the diagonal. We're just interested to see if its square length is 5. So we compare all these values with 5, and that gives us our Boolean mask. And then, just as before, we ask, where are these ones? And that gives us our solution. Thank you for watching.